Okay, welcome back, everybody. We are looking at section 10.6, which continues our conversation about hypothesis testing, and we get to introduce a brand new test, which has to do with the chi-square distribution. And this is the chi-square test for goodness of fit. So yes, it's not pronounced P, it's pronounced I. Okay, so we do want to make sure we pronounce it correctly. It does have Chinese origin, and so we want to make sure that we give it the correct pronunciation. As with the other videos that I have created, these are all coming from at least the examples, all or in part, from the Hawks Learning System. So again, making sure I'm citing my sources. All right, so at the completion of this section, you should be able to write a hypothesis based on a given scenario. And you might say, well, I have some familiarity with writing hypotheses already. That's great. From the previous sections, there are a little bit of changes that we need to take into consideration. You should be able to compute the test statistic and degrees, I should say, of freedom, not for freedom. Find the critical value of the chi-square chart, make a decision and write a conclusion for the hypothesis test, and of course, be able to carry out a full hypothesis test for this particular context from start to finish, as will be the expectation for homework, exams, and the final. All right, so we have to remind ourselves these are the steps to the hypothesis test that we are familiar with from prior sections. We have a little bit of changes, okay? So the first step remains unchanged, okay? It's still write the hypotheses, but step 2 now is to compute not a test statistic or z-score, but it's the chi-square test statistic, and the computation is a bit tedious for doing so by hand. Step 3 used to be finding the p-value. In this case, we are going to use the chi-square critical value. So it involves a different table, and it requires something called the DF, or degree of freedom, and alpha is back. Good news there. Step 4 is still the decision, but we have a little bit of different criteria. We need to compare the test statistic to the critical value, not the p-value to alpha. Okay, it's like we're used to before. And step 5 remains unchanged with the conclusion. So some changes that we need to think about. So we'll examine this in a few minutes. Now, there are two cases that we consider with the chi-square test for goodness of fit. And the first is to compare a frequency distribution that you have familiarity with from chapter 2 that an experiment produces with what theoretically should be expected. So the frequency distribution would be considered what we call observed values. So what is it that we observe? How well does that fit with theory? Theory is what should be happening. So how well do the two match? And the second is to assess whether the two traits or characteristics in a population are associated in some kind of way. Okay, so this idea of characteristics, this comes up with section 10.7 for the test for association. So section 10.6 handles number 1, section 10.7, which is the next video, handles this second case, okay, for the chi-square test that we look at. Now, we do have some technicalities with this. First of all, we assume we have multinomial experiments. This means we have fixed number of independent trials. Probabilities for the categories remain consistent for each of the trials. The test assesses what we call how good, quote unquote, the sample distribution and theory distribution sort of fit or match each other. That's the idea with section 10.6. How well do they fit? Okay, so let's look at an example to try to understand a little bit of these ideas. So let's suppose we want to test if a die, a 6-sided die, is actually fair. So that is to say, it's not tampered with in any way. So you want to know whether the distribution of rolls obtained from the test die match what theory is going to tell us. Okay, so let's make sure we understand this. So if we record the outcomes of rolling the test die 100 times, we could compare them to the outcomes we would expect for a fair die. So in other words, we would expect each number on the die to be rolled about 1/6 of the time, okay? And the reason is because the probability of rolling one of the digits on the die would be 1/6. If you remember back to chapter 4, we call that the classical or theoretical probability. Chapter 4 is coming back, okay? Now, with us recording the number of outcomes over 100 rolls, that we would call the experimental probability. Do you guys remember that? I hope you do. Okay, this is kind of getting to the idea of the law of large numbers, right? Where we would expect, what we expect is the number of times the die comes up in 100 rolls, okay, for a specific digit, let's say 3, we would expect it to come up 1/6 of the 100 rolls. Okay, that's the idea here, right? The more times we roll that die, the more frequent those die numbers come up should approach each probability of 1/6. Okay. So if we're rolling it 100 times, what should happen is that we should have for each of the 6 values, each should be showing 17 times if this is actually accurate. So number 1 should come up 17 times, number 2 17 times, number 3, 4, 5, and 6, all 17 times. This is what theory is telling us should happen. Okay, so that would imply that the die is actually fair. Well, here's what reality says. So somebody went and conducted this experiment, okay? And what we see is how many times each value actually did come up in 100 rolls, okay? Now you see on here, you say, all right, well, not everything came up exactly 17 times as we predicted with what theory says. So is this are these results, are they close enough for the die to be considered fair, or are these way too off that we need to declare the die to not be fair? So that's the question that this hypothesis test can certainly answer. Now you might say, well, what's going on with number 3 on this particular die only coming up 8 times? What I would say is maybe we need to roll this another 100 times and see what happens. Okay, that obviously will change the expected count. We would have to take 200 times 1/6 to see what that expected count would be, and make sure that each of the frequencies matches that new number. So that expected count would have to change depending on the number of trials that we ran this for. But the idea is, by the law of large numbers, these should all be 17. Interesting. So that's what this test helps us to understand. Are these going to be fit? Does theory and reality fit? Okay, so in a chi-square test for goodness of fit, we have to consider the 2 hypotheses, the null and the alternative. So the null hypothesis in its basic form is that the observed values match the expected values. So in other words, everything is wonderful, okay? Observed matches the expected. The alternative says they don't match. The observed values and expected values don't match. So remember, observed is reality, what's happened, the actual data that I collect. Expected is theory. Okay, so how well does reality match theory? Okay, reality and theory. Okay, now we have 2 cases that we look at for the hypotheses. The first case is when the theoretical probabilities for the outcomes are all the same. The hypotheses are then stated as follows. So what we do for the null is we say that P1 is equal to P2 is equal to, well, however many we have. Okay, and the alternative is that there is some difference among those probabilities. The second is if the theoretical probabilities for the outcomes are not the same, what we have to do is we have to list them separately. So in other words, you have to say the probability of 1 is equal to whatever that value is, let's say 20%. Probability of the second outcome is equal to 30%, all the way up to however many outcomes you have. Okay, so a little bit more tedious to list out. And you'll notice that the alternative is also the same. Is there some difference amongst the probabilities? So really the hypotheses that we need to be concerned with in this test is the null. Are all the probabilities the same, or are they different? Okay, so we will work an example with each because there is an implication that we need to consider a little bit later. It is important to make sure that all the probabilities do sum to 1. Okay, and if you're wondering why, I'm going to refer you back to chapter 4. Now, from our example about the 6-sided die, we remember, or should remember, that each die, each value on the die has an equally likely chance of coming up. So 6 outcomes, each having 1/6 chance. So the hypothesis that we would use for this particular situation would be case 1, where P1 would be equal to P2, which would be equal to P3, et cetera, all the way up to the 6th outcome. And I could also write here would be equal to 1/6. So this would be the case where all the probabilities are the same. The alternative would be there is some difference amongst the probabilities. In other words, they're not all the same. Maybe a couple are, but others would be different. All right, so let's understand this example. I'll give you an opportunity to pause and read. I won't read this all to you because what we're going to do here is write the hypothesis. So pause the video and give this one a read. Okay, in this instance, what you should notice is we have four colors, okay? Green, yellow, red, and orange. And it's indicated in the problem that there are different percentages for each one. Did you notice that? 20% for green, 40% for yellow, etc. So these are not equally likely. Okay, in the previous example, they were. The die values coming up were all equally likely. So this means for this particular hypothesis, we would have to use the second case. So for the null hypothesis, look how I listed them. I have to list them separately. And I use a subscript to indicate the color. Okay, so this way it's clear for my audience. So I use probability of green is equal to 0.2, probability of yellow is 0.4, etc. All those probabilities should sum to 1, and they do. And you'll notice the alternative is that there's some difference amongst the probabilities. So again, difference between the first one, they were all equally likely. This case, they were different. So I have to explicitly list them. So there is something you will have to pay attention to when you read these questions. Now, next, what we're going to need to do is compute the test statistic. And this can be a little bit cumbersome, okay, depending. So we have some considerations that we have to take into account when we compute the test statistic. And they're on the screen here for you to read. So you're welcome to pause and to take a look at this. Now, we do have a formula for the chi-square test for goodness of fit, and this is what it looks like. Okay, so the symbol that we use for chi-square looks like a fancy X, and it's squared. Okay, that's the variable chi. Sigma you should have familiarity with. It means sum. Okay, we've seen that before. So OI references observed frequencies. Okay, and I represents the number of the outcome, first outcome, second outcome, third outcome, etc. The E stands for the expected frequency, okay, for that outcome. So every observed outcome has its own expected outcome. I didn't use the word unique because it doesn't necessarily have to be unique. It could be the same expected outcome for all of them, or there might be some difference. And I'll illustrate what I mean in a few minutes, okay? But for now, this is our formula. Computing it can be a little bit challenging, which we'll talk about. Now, there's one other thing that we're going to need to do in this test, and that is to use what's called a degree of freedom. Okay, a degree of freedom has relationship to sort of the sample size. In other words, in this case, the number of categories that we're going to be looking at. So in the previous example, that would have been four colors. Okay. And what it helps us to do is to define what the chi-square graph looks like. The chi-square distribution is known as a family of distributions. And the reason we call it a family of distributions is because there's no one set shape of the graph. It depends on, again, the sample. In other words, the number of categories that we're dealing with. So that's why there's a little bit of a difference from the normal distribution. Normal distribution was just a single graph, beautiful. This one, not the case, a little bit fancier. So in this instance, we have a formula for the degrees of freedom, and that is k minus 1, and the k is the number of possible outcomes or categories for each trial. Okay, so rolling the die would have been 6. In the case of the colors that we looked at a few minutes ago, that would be 4. And what we use then is the critical value of the chi-square distribution to help. And so what we have to do is to go to the table of values with our degree of freedom and a given level of alpha. Alpha, remember, was the level of significance. Now we have some decision criteria that we have. This is a bit different than last time, okay? Last time, if the p-value was less than the alpha level, we rejected the null. Here, what we're looking at is if our chi-square test statistic that we compute is less than the critical value, we fail to reject the null. And if our statistic is more than the critical value, then we reject the null. And everybody gets a little confused as to why this is the case. And I'll explain that when we look at some context in a moment. This is an excerpt of the chi-square table that is found on the formula sheet. A couple of things to note out for you. First is the leftmost column is labeled DF. That is the degree of freedom, okay? And this goes all the way down the page. There's a lot more, okay? And across the top is the level of significance, okay? The alpha level. So if, for example, I wanted to find the critical value for chi-square with a degree of freedom of 9 and an alpha level of 0.025, what I'd look for, first of all, is the degrees of freedom is 9. That locks me into the row. And the alpha level of 0.025 locks me into the column. And so the value that I would use for the critical value would be 19.023. So that's how we use this table. Some people argue it's a little easier than the normal table. We don't have to worry about positives and negatives, which is true the case. There's only one table that we have to look at. Okay, so that would be our critical value. Notice how I wrote it. I used a subscript CV to stand for the critical value. Critical value means it's coming from the chart. If we said test statistic, that's something that I'm computing. I put my hands on it. I worked on it. Okay, a little bit of a difference. Okay, let's look at an example and try to work this all the way through. So again, I'm going to let you pause the video and read this for yourself. All right, hopefully you've had an opportunity to read through the problem. And so the idea here is that we are trying to figure out how busy this ATM machine is on particular days. And so we have a frequency distribution that is being shown to us here. So one of the things you're going to have to do on homework, final exams, etc., is to figure out, number one, is this a hypothesis test? And, how do we know which test it is? So reading this question, you obviously do not see anything regarding the word mean or average, and certainly no proportions listed anywhere. Okay, so pretty easy to see that this would have to be a goodness of fit test. The other clue is that we have a frequency distribution listed here. We have the days of the week, and we have the number of times that the ATM was used. That is a frequency distribution. If you don't remember how frequency distributions work, I would refer you back to section 2.1. Okay, so the first step is to get the hypotheses. Now notice that in this particular problem, it does not specify percentages for each day of the week. So I'm trying to decide which of the two cases for the null hypothesis that I have to deal with. Now, it is impossible for one day of the week to have a different probability than another day of the week. So they're all equally likely. So this would lead us to a case one null hypothesis, okay? So the text likes to offer the hypothesis in words. So one way of considering this is to say the following. The proportions of customers who use the ATM do not vary by the day of the week. And the alternative would be the proportions of customers who use the ATM do vary by the day of the week, okay? Now, to better fit case one's format and what would be a little bit more preferred would be the following. So this would be the null hypothesis is P1 is equal to P2 equals to P3, and there should be P7. So if you're writing this one out, make sure you put equals P7 because there are 7 days of the week that we need to consider. So I apologize for that omission. So again, should be equal to P7, which is equal to 1/7, 7 days of the week. And the alternative here would be there is some difference amongst the probabilities. Okay, that again is the standard that we use for the alternative hypothesis. So again, all of the probabilities here equally likely, all 7 of them. Now, our test statistic for step 2 is this particular formula. And what we need to do is to figure out what the expected count is. And thankfully, this is easy for this particular test, since we know from the null hypothesis that all of the days are equally likely. So the expected count for Monday is going to be the same as Tuesday, Wednesday, Thursday, etc. And the formula that we have for the expected count is n times p. So the n of 242 came from me adding up all the times the ATM was used from that frequency distribution. We multiply that by 1/7, okay, since we have 7 days of the week and it's all equally likely, and we get a value of 35.571. So the good news is that this expected count is going to be the same for every single observed value in this specific test. Okay, so here it is. So what we do is we take each observed count. So from the chart, the first count was 38. I subtract its expected count, which was 34.571. square that difference, and I divide by the expected count. And I repeat this process for all the other observed counts in the chart. And you can see that this would be a very tedious thing to have to do on one's own and by hand. Okay, so you all need to be very nice to me in class. This way I don't give you one on the exam that has, I don't know, 20 of these. Okay, you'd have 20 of these fractions you'd have to, compute out. That would be a lot of fun, wouldn't it? All right, maybe not. All right, I did the computation myself, and this comes out to about 12.314. Okay, so again, the expected counts here are all the same, so that's the good news. All right, step 3 is to figure out what the number of degrees of freedom are for this particular test. Now, in this case, the degree of freedom formula is n-1, and the n here is the number of categories we have. Now, this is easy. Go back to the null hypothesis, and you should have listed P1 is equal to P2 all the way up to P7, okay? And since it's 7 days of the week, n has to be 7. So the degrees of freedom here is 7 minus 1, or 6. We have an alpha value of 0.05, degrees of freedom 6, so you need to go and find what that critical value is from the chart, which is 12.592. So just to make sure that we're all on the same page about this, there's my degrees of freedom, there's my alpha level, and there is the value in particular for our critical value. Now, step 4 is that we need to make a decision. So we need to compare the test statistic to the critical value that we have. Okay, so there's my statistic versus the critical value. So the statistic, remember, is the value we computed. Okay, so the stat is what we put our hands on. We computed all by ourselves. So that's 12.314. We notice that is less than 12.592. Okay, which was the value off of the chart. So what we have to do here is to fail to reject the null hypothesis. We needed our statistic to be more than the CV, not less. Now here is why. If you look at the picture at the right, you'll notice that we have 12.592 that's listed in purple, okay? That is the value from the chart, and the values to the right of that defines what we call a rejection region, okay? So there's my 12.592. So this is the rejection region. I want my statistic to fall in there. So in other words, I have to be more than 12.592 to be rejected. Unfortunately, I don't. If you look at the green, 12.314, it's less. It's not in the rejection region. It's in the fail to reject region. Okay, so that's the way the cookie crumbles here. So we have to fail to reject the null hypothesis. All that hard work, and it's not enough. Now, step 5 is to write the conclusion. And so I want to recall what the problem said is that she decides to use statistical inference at 0.05 level of significance to test a customer's claim that the ATM is much busier on some days of the week than it is on other days of the week. So we failed to reject the null. So the failing to reject the null means that all of those probabilities are equally likely, which means that the ATM is used about the same every day. So the customer is not always right, okay, in this instance. So the customer, unfortunately, is incorrect. So at the 0.05 level of significance, there is not sufficient evidence to support the customer's claim that the ATM is used significantly more on any particular day of the week. Okay, and that's a completed hypothesis test for goodness of fit. I want to do one more with you. I actually want to return to the example that had the children's vitamins. So give yourself a second to read this, and we'll proceed through this one. Now, in this particular instance, again, how do we know that this is a hypothesis test? That should be obvious with alpha and sufficient evidence, et cetera. Okay. Now, the other part is how do we know that this is a goodness of fit test compared to the other tests that we've looked at? So again, it doesn't use the word mean anywhere in here or average. And in terms of proportions, I actually see 4 of them. Okay, we haven't dealt with 4 proportions in the prior hypothesis tests that we looked at in the other sections. Ultimately, we also have a frequency distribution here too. We haven't seen one of those in the prior hypothesis tests either. Okay, so again, just looking at some context clues here. So this would definitely be a goodness of fit test. And again, we have 4 categories, and we're trying to see how they fit with these observed counts. Okay, so now if you notice, we listed out explicitly what the colors are and what the percentages are. Okay, this is different than the last example. The last example, we had days of the week. In this case, we don't have equally likely chances because each of the colors has a different percentage. So this means we're using case 2 for the hypothesis in this section. So unfortunately, I'm going to have to list all of them out explicitly, and there they are. Okay, so I have to list these out explicitly. Now, people say, well, is that going to have an impact on the chi-square test statistic? It is. It actually makes the computation of the test statistic a bit more difficult. What we have to do is compute the expected counts separately. Okay, we can't say that they're all the same. And the reason is because the percentages are all the same. So the first thing we need to do is find n, which I've done for you, is 5,050. And now we need to use the expected count formula, n times p, for each of them. Okay, so there they are. So the expected count for green is 1010, for red is 505, yellow and orange are listed there. So what you're going to have to do now is when we compute the test statistic is you need to make sure that you match the observed count with its correct expected count. Very, very important. Okay, so here's what the values end up looking like. So the first the first observed count was 1149. It gets matched with its expected count of 1010. Okay. Next is 1948, matched with its expected count of 2020, etc. So these have to match. Okay, if you want to double check the computations, you're welcome to. It comes out to about 34.65, okay, for our test statistic. So again, this one a little bit more challenging because each expected count is different. Okay, is different. Okay, step 3 is our critical value. So for this, we need the level of significance, which was provided as alpha is 0.05. And what is K? K is, well, the number of categories we have. So if you look back at the null hypothesis, there were 4 colors. So 4 is going to be K. And our degree of freedom then is 4 minus 1 or 3. And the value off the chart is 7.815. Okay, and you're welcome to verify that on the chart. Step 4 is the decision. So what we need to see here is, is the statistic less than the critical value? No, that inequality should be the other way. My goodness, okay? So the chi-square test statistic is more than the critical value. Sorry about that. Make that correction there. Okay, make sure folks are paying attention here. So 34.65 is more than 7.815. So we reject the null hypothesis. That's what we want. We want to be in that rejection region, okay? So that's the good news. We get to reject the null here. So our conclusion is at the alpha is 0.05 level of significance, there is sufficient evidence to conclude that the percentage stated by the vitamin manufacturer are indeed incorrect. And that's because we are rejecting the null hypothesis here. So 34.65 is greater than 7.815. Very, very important. Now, there is another way that we could have used to compute the test statistic, and it's known as the chart method. I talk a bit more about this in section 10.7, but you're welcome to use it as well. So if you didn't like listing out all those fractions, you could have organized things in terms of a chart. And so that's what I'm demonstrating here. So what you should notice is on the left side, we've listed all the observed values. Then we list the expected. Okay, and I work the first column so you see where the values are coming from. So I took 50/50 times 0.2. 0.2 was the 20% for that color, and got 10/10. Then I did the observed value minus the expected. Then I squared it, and then I took that value and divided by the expected. And then I summed that last column to get the 34.6485. So if this makes more sense to you to use a chart to compute that test statistic, you're certainly welcome to use that if you so choose. All right, so recap on section 10.6. So do note the difference in the wording for these hypothesis tests, and certainly the inclusion of a frequency distribution table in some of the examples. Also be mindful of the two cases for the null hypothesis and the implication on the computation. So in other words, looking and comparing the two hypothesis tests that we've done so far. Do make sure you take your time with the computation of the test statistic. It might be better for people to use the chart method if you don't want to list out all those fractions separately. And certainly be mindful of the decision criteria. We need that test statistic to be more than the critical value, okay? And do take note of all 5 of those steps.